Thank you for being part of our lecture series 24, part 2, Divergence and Curl. We have been covering vector flow, vector forces, and now we're covering also divergence. So we wanted to do an example for you. Okay, we see here, we have, and we showed the difference between a regular derivative and a gradient and a divergence. Okay, so what we have here is a function, and this is what is emitting out the forces. So it's like the sun, it's the rays from the sun, like a shower, like the water from the shower. Many different applications that you can utilize this in. So what we need to know is that the divergence of a function, if it's greater than 0, then the net flows away from the point of this, and we call it a source, from the source of where the energy is coming from, the water is coming from. Now, if the divergence is less than 0, then the net flow toward the point is what we call a sink. Well, let's give us an easy example. Xi plus yj. Okay, let's see what this represents. We can see that this will be taking the partial respect to x. For f of x, you get 1, and you take it for y, and you get 1, and 1 plus 1 is 2. So you're going from a vector f with the ij components to a scalar with no components. Okay, it's just the flow. So we see here that the divergence is equal to 2, which is greater than 2, then its net flow is away from the source. So it's like a shower head. It's like the sun's rays. Okay, literally think of the source and the sink as if they were like a faucet, or like the shower head, like I said, or like the sun, or you can look at it as raindrops falling on my head. Okay, you have raindrops of water falling on a plane, or as we said, the drainage out of a sink, out of a bathtub, out of a sink. Okay, that goes away. So, what alternative that we have? You can find meshes, a mesh, okay, that has different holes, various hole size, and it lets out all the water, as an example. So note that if the divergence of a function is equal to 2, this does not mean it's just a source or a sink at the origin. It can be anywhere. It doesn't have to everything that start at the origin. We are adding flow everywhere, not in one spot. Think of the fine rainfall covering the planet. Now, the rain is coming from every place under the sun. There's no question about that. The rays of the sun is coming from every rays from every direction also. So keep that in mind. So here's another example of divergence. Now, remember, we have to remember that if the divergence is greater than 0, it's called the source. It's away from the point. If it's a less than 0, then the net force is a sink. It's going toward the point. So we use a different example, a minus yi plus xj. So we're switching the x and the y's, and now with different components, and also a negative in front of the j. So you see here, if we take the partial of this, and we take the partial of this with respect to x is 0, take this with respect to y is 0, respect to there is 0, 0, 0, so everything is 0. So no source or sink. Okay, so then if there's no source and no sink, what is actually happening to it? Let's see. Aha, it's a circulation. It's a circulation. Okay, so we've been looking at a few things, trying to see what makes sense and what does not. Okay, let's go to another example. Okay, remember this is the divergence formula. Remember, if it's greater than 0, it's a source. If it's less than 0, it's a sink. So we're just going to use it equal 5i. There's 5 in the x direction. Okay, so if you take the derivative of 5, a constant, you get what? 0. Okay, so now, what is this one? Okay, it's all going in one direction, clear. Okay, this example of 5i is just, all going in that one direction. So what does it look like? It's a beam under compression, that's stress, capacitors, and a field, magnetic field. There you go. We have it. So you see that there's many different ways that we can actually perform this. Okay, we're just covering divergence now, and later on we'll be covering curl. Okay, so what is the neat features? Okay, we got some neat features here. Okay, if you have your rho and your velocity, okay, and you multiply it times del, okay, you'll get the partial of t with respect to the density. This is the change in the density. So that's what the major factors is, change in density. So we have here this as the source, and it can be a sink density. Then if we want to, we just take case 1. We just take one case. We've got 2 different cases, at least. So let's take a look at it where we have this equal to 0. Then there is no source or no sink. Therefore, we can have, because this is all in reference to the density, we can have our divergence, then our divergence plus the change in over time for rho is equal to 0. So let's look at case 2. Case 2 is if we have the delta change over P or over rho, and that's equal to what? 0. So if you set that equal to 0, then what happens? Then you have incompressible fluid or static electricity that you're modeling. Okay? So now what you have is that you have the divergence of rho times velocity, and for electrical field, we have this change in density. Now look here, we have the density of epsilon of 0. So that means, I think that's the for air. Okay. Now notice what we have here. We're taking the del dot the E field with this constant of permittivity, I believe. Permittivity. Okay. And so it lets us know that this same formula is what we use in a Gaussian law. And that's how we are able to use the what? Delta dot E. Then we also have something that looks like the magnetic field, okay? And we can set the magnetic field equal to 0. There's no magnetic charge density, okay? These are things that you should have remembered, because that's basically what we're doing. Same thing we did in physics, okay? No magnetic charge density. Okay, and this is the Gaussian law of magnetism. Okay, so we have here another example for the field of F at x, y, z. Very simple. It's x, y, z, x, I, j, k. Okay, calculate the integral, okay, of the volume of the divergence, plus you need the volume, over the volume of the sphere of a radius of A. And so when we take this equation, we look at it partial respect to x. For x is going to give us 1, same thing for y, same thing for z. So it's going to add up to give us what? 3. Okay, so now we're taking the what? We're taking the divergence, which we did. Now we're going to multiply it times the volume, so we can see how much of it, the rate of it is going out or in, or how is it actually flowing. Okay, and we're just using 3 for the sphere also of the spherical coordinate system. So we remember correctly that we go from 0 to 2, 0 to pi, and from 0 to a. And we have the 3 that we're putting there, because that's what we came up with. Okay, then there's r squared sine of theta, or dr, d theta, d phi. And so what we have here is 3 volumes of a sphere. Those 3 of them. Okay, we had 3, and we found out last time we studied, when we were doing gradient, we found out that it was equal to 4 over 3 pi a cubed. So it's nothing but 4 pi a cubed. Nothing spectacular. Okay, at this time we will let you break, and you will go start working on practice problem number 1. Okay, thank you for being part of our study and being part of part 2.